Okay, so in this video lecture, we want to talk about L'Hopital's rule. So this is a way to easily evaluate limits. So remember before we had this method of factor and cancel or rationalize the numerator or denominator. And we did that whenever we got a form 0 over 0. So if we just plug the number into the function and we got 0 over 0, that's what we called an indeterminate form. And that was sort of a clue to let us know that we should do some algebra to try to rewrite the function in a way that's more convenient. So there are several indeterminate forms that when we see these, we want to try to apply a rule called L'Hopital's rule for evaluating limits. So here's what we mean by indeterminate form, or at least these are the ones that we're allowed to apply the theorem. So the first two, these are the main ones, right? So item 1 and item 2 would be sort of the main indeterminate forms. And all of these others, at some point, we will try to write them so that they have indeterminate forms, item 1, or indeterminate form like item 2. So 0 over 0, we've seen that plenty of times. When we looked at limits at infinity, we certainly had the form infinity over infinity. And then we've got 0 times infinity. That's not necessarily 0. If the strength of the infinity is more than the strength of 0, in other words, if you've got a product of two functions and one goes to infinity faster than the other one goes to 0, whatever that means, then this thing might not be 0. So we want to be really careful here. And the same thing here, infinity minus infinity. One of these infinities might be stronger than the other one, and so this is not necessarily 0, right? 0 to the 0, what does that even mean? I mean, anything to the 0 power is 1, but the 0 function is just 0, so this is sort of, right? We don't know what this is, so some more work to do. Infinity to the 0 and 1 to the infinity, right? These are all indeterminate forms, and we want to apply this L'Hopital's rule to forms where one of these situations will occur to try to, right, make things better, get us out of that form if we can. Okay, let's write down L'Hopital's theorem really quick. Okay, here's what L'Hopital's rule says, and we want to be careful that we understand exactly what it says so that we know when we can apply this thing and when we cannot. So we've got two differentiable functions, f and g. So suppose f and g are differentiable functions on an open interval or on some interval I containing the point x equals a. And suppose also that g prime of a is not equal to 0. So you take the derivative, plug in a, you don't get 0. If both of these limits exist, so the limit as x approaches a of f over g, and the limit as x approaches a of f prime over g prime, or if we go to infinity, either one, right? If both of these limits exist, and they've got the form 0 over 0 or infinity over infinity, so that was indeterminate form 1 or indeterminate form 2, then these two limits are in fact equal. So in other words, I can evaluate the limit on the left-hand side, so the limit as x approaches a or x approaches infinity of f over g, right? That's the same thing as the limit as x approaches a or infinity of f prime over g prime. So a lot of times, you can simplify a function by taking its derivative, right? At least in the case of polynomials, right? You can knock the power down a notch by taking derivatives. So that might turn out to be useful. So let's have a look at a few examples of L'Hopital's rule. And by the way, we want to use this when we get to the section on advanced curve sketching so we know what the vertical and horizontal asymptotes look like. Because if you remember back to the beginning of the semester, right, horizontal asymptotes were limits as x goes to infinity, and the vertical asymptotes, you found that by looking at the limit as x approaches some point a. And also you can get a feel for what the deleted points look like, right? If there's jump discontinuities or removable discontinuities, that kind of thing. Okay, a few examples. Okay, here's an old familiar example. The limit as x approaches 1 of x squared minus 1 over x minus 1. So if you try to plug in 1, that doesn't work. So you get the form 0 over 0 here. So that's one of the indeterminate forms, and that indicated that maybe we should try some algebra to rewrite this thing in such a way that we can just plug in a 1. So we factor the numerator, and we get x plus 1 times x minus 1 over x minus 1. The x minus 1s cancel, and because these two functions are equal everywhere except at the point x equals 1, these two limits are equal. So this limit as x approaches 1 of x squared minus 1 over x minus 1 is just equal to the limit as x approaches 1 of just the regular or linear function x plus 1. And we can certainly plug a 1 in for x, and when we do, we get a 2. So that's how we used to compute limits in the beginning of the semester, before we knew about derivatives, right? So now, what about the limit as x approaches 1 of x squared minus 1 over x minus 1? Again, the indeterminate form 0 over 0 says that L'Hopital's rule does apply because both of these limits should exist, right? So we can just take the derivative of x squared minus 1, right? Not the quotient rule, just the derivative of the top and the derivative of the bottom. So the derivative of the top is just 2x. The derivative of the bottom is just a 1. And so by L'Hopital's rule, I'll put a little h for L'Hopital, for L apostrophe Hopital. So by L'Hopital's rule, I know this limit is just equal to this limit. So certainly you can just plug in a 1 and you get a 2, right? So that's fairly straightforward. So maybe we get the feel here that this L'Hopital's rule actually works. Okay, let's look at a few other examples just using L'Hopital's rule. Okay, here are 3 very easy examples. Well, 2 examples and 1 non-example. So the limit as x approaches 1 of natural log of x over x minus 1. If you plug in a 1, you get 0 over 0. Both of these functions are differentiable at the point 1, and so we can take the derivative, right? So we got the good indeterminate form. That means we are allowed to apply L'Hopital's rule. The derivative of natural log of x is 1 over x. The derivative of x minus 1 is just a 1. Now you can plug in a 1, so you get 1 over 1 over 1. That's just a 1, right? Very straightforward business here. Here the limit as x approaches infinity of e to the x over x squared. Again, you get infinity over infinity. So that's one of the forms that we are allowed to apply L'Hopital's rule. That was the second indeterminate form. So apply L'Hopital. The derivative of e to the x is e to the x. The derivative of x squared is 2x. So again, you try to plug in an infinity and you get infinity over infinity. Again, that's indeterminate form, the second kind. L'Hopital's rule still applies. So let's carry it out one more time. So here I get e to the x, right? And the derivative of 2x is just 2. So now we've got infinity over 2. That's not one of the indeterminate forms. But we know as e to the x gets large, dividing that by 2 still gets large. And so positive infinity would be a good final answer. So we know that this graph just goes off to positive infinity for its end behavior, right? So in this case, there wouldn't be a horizontal asymptote. And then the third example here, limit as x approaches pi from the left of sine x over 1 minus cosine of x. Well, remember, always try to just plug in the number, right? So don't just take derivatives right off the bat. Plug in the number first. So we plug in pi, we get 0, and we plug in pi in the denominator here, we get 1 minus negative 1, so that's a 2, so we get 0. So L'Hopital's rule does not apply. If you try to take derivatives here, right, in the numerator you get a cosine, in the denominator you get a positive sign, and so if you plug in a pi, you get negative 1 over 0, and so remember, if we get a non-zero over a 0, then we know that the answer should be plus or minus infinity. We just need to figure out which one, if you remember the videos from the beginning of the semester. So cosine of pi is -1, and then the sine of, well, when we approach pi from the left, the sign will return positive values. So it's negative over a positive, so that should be a negative infinity. Right, negative infinity is a far sight different than 0, right? So if you try to take derivatives right off the bat, you will get the wrong answer, right? The answer to this thing is 0. Okay, let's look at some more advanced examples in the next videos.